evening. For the first time, we have actual pictures of planets orbiting another star, in this case 130 light years away. And this is a real breakthrough. Well, earlier this year, Chris went to California to talk to Professor Geoff Marcy.
It's summer in California, providing views of a hazy San Francisco Bay. The University of California, Berkeley, is home to a whole host of astronomers, and I'm here to meet one of them, the planet hunter, Geoff Marcy. So, Geoff, what's the plan for this evening?
Well, we're going to continue observing about 40 stars, nearby stars, hoping to find Earth-like planets, planets a little more massive than the Earth that remind us of home.
And how long have you been looking at these stars?
About 10 days now.
On a quiet Sunday afternoon on campus, we've caught Geoff at the end of an observing run, using one of the Keck telescopes on Hawaii. With the discovery of planets around other stars now a regular event, it's easy to forget just how new this science is. The first extrasolar planet was discovered only 13 years ago. The Holy Grail is to find a rocky planet, like our own, but so far they've had no luck. The closest we've got so far is to find planets about 5 times the size of the Earth. In fact, the planets we know of are almost certainly all large gas giants.
Well, remarkably, we've found planets larger than our Jupiter, which is, of course, the biggest planet in our solar system, planets the size of Saturn. We're beginning to find planets the size of Neptune and Uranus that are about 15 times bigger than the Earth. And slowly but surely, we're beginning to find planets smaller and smaller, almost as large as the Earth itself is.
You said almost as large, but these are all larger than Earth.
Yeah, the smallest planets we've found so far are a few times the mass of the Earth.
So what would you have seen from a nearby star? If you were looking back at the solar system, what would we have detected?
Well, if we looked back at our solar system as seen from, let's say, Alpha Centauri, a star system nearby, we would easily detect Jupiter, hints of Saturn. We would not have been able to detect the Earth, Venus, Mercury, Mars, and so on. So the real excitement is finding the rocky terrestrial planets that so far would have eluded our detection.
Can we point to a random star and say how likely it is that it has planets at all?
I believe when you look up into the night sky and you see the twinkling lights, 15% of those stars have Jupiters like our own. Maybe another 10 or 15% have Saturns. The remaining stars, all, I suspect, almost all, have Earths, Venuses, Mars, rocky planets that remind us of the terrestrial planets here in the solar system.
As Geoff and I talk, on Hawaii, the giant Keck telescope is being prepared for the night, ready to direct its 10-meter mirror in the search for rocky planets.
Well, the interesting thing is that our Milky Way galaxy within which we live contains 200 billion stars. Certainly we can't examine all of them for planets. So what we do is we examine the stars that are closest to our Earth, the ones that you can see with your naked eye and a little bit farther away, out to about 100 light years or so. And the reason we do this is that, frankly, we astronomers are starved for photons. We need the light to analyze that light and therefore discover the planets. In fact, we have many selection criteria for our stars. One is that they be close and therefore bright. Another is that middle-aged stars and older are better. Middle-aged stars are more quiescent. They're more docile. They don't have magnetic flares and star spots and crazy activity that characterizes the youth of stars. So we frankly avoid young stars. Stars younger than about 2 billion years old we consider too young to easily hunt for planets.
So if these things are common, if rocky planets are everywhere, why haven't you found them yet? Why isn't your job done?
Well, you know, the interesting thing is that our sun outshines the Earth by a factor of 10 billion. So if you point the Hubble Space Telescope at a nearby star, the poor Earth, even if it's there, is lost in the glare of the host star. So we really don't have a good technique quite yet to detect true Earths.
And so instead we have to look at these things indirectly.
Well, there are 3 brilliant techniques that have all been successful now in finding medium-sized and bigger planets. One of them is the now famous Doppler technique, in which a star is yanked gravitationally by a planet, and so you simply watch to see if the star wobbles in space by the Doppler effect. A very exciting new technique in the last few years has been to watch stars to see if a planet crosses in front, dimming the star as the planet transits the face of the star, and that dimming of the star can be measured. And then most recently, some planets have been discovered by gravitational microlensing, which is a fancy word meaning that the light from a background star bends because of the gravity of the planet, and we can see that bending of the background starlight telling us that a planet is there.
The first planets were discovered back in 1995. When did you get involved in this game?
When I told colleagues back in the 1980s and 90s that I was going to be hunting for planets with some new technique, they would look down at their shoes, embarrassed, scuffle their feet, and change the subject. So it was an embarrassing pursuit to look for planets back in the 80s and 90s. It was akin to hunting for pyramid power or telekinesis, and so an upstanding, proper scientist didn't hunt for planets.
Well, you had the last laugh there, I think. Tonight we're using the Keck telescope, so what's the plan? What shall we do with it?
Well, we have a sample of about 40 stars that we've been watching very intensely now for, frankly, about 2 years. But now we're on a 10-night observing run. We've been using the Keck telescope every night. This is night 8 of a 10-night run. And we're monitoring the Doppler shifts of these stars. And in fact, we have a few candidates that we're very excited about. We still need a few more measurements to be absolutely sure. But as you can imagine, with all of this effort, we have a little twinkle in our eye.
It's now dark in Hawaii. In the basement at Berkeley, Geoff can check his first results, while 2,000 miles away, the telescope moves from star to star.
There we go. All right. This is the second hardest star of the night. That's really good.
Mm-hmm.
Okay, set to go.
Sure.
Great.
There it is.
It is. Yes. That looks good. This computer screen tells us the coordinates where the telescope is pointed. This computer screen tells us the data as it comes in. And what we do here at the back of the Keck telescope, instead of having an eyepiece, we get rid of the eyepiece and the light instead goes through into a spectrometer, spreading the light into its composite wavelengths or frequencies of light, and we store them digitally and then analyze those frequencies of light for the Doppler effect that allows us to find planets.
How long do you look at each one for?
We'll spend 3 to 5 minutes on each star, something like that. The fainter ones, 8 minutes even. Brighter ones, 1 minute. So, Joel, could you give us a little summary? What do you think the weather's like outside?
I think it's, broken cloud. Let's see we got a couple of minutes, right? You go have a look.
I always find it curious that when we're looking for the wobbles of stars, we're really trying to detect an effect that Isaac Newton would have appreciated 400 years ago.
It's just his physics.
Just Newtonian physics. You don't need Einstein, you don't need Max Planck. You just need good old Isaac. And of course, one of the most famous laws from Isaac Newton is that for every action, there's an equal and opposite reaction, and that's exactly what's happening. We all know that the Earth orbits the Sun, and here what we're trying to detect is the Sun being jerked around by the orbiting planet. That's the reaction.
Discovering planets takes time, but we've just heard that preliminary results from Geoff's observing run in June led to the discovery of 3 new planets. That's 3 more needles plucked from the haystack, and progress in searching for planets has been spectacular. Only a few weeks ago, the Hubble Space Telescope released this image of a planet moving in a dust disk around the young star Fomalhaut. Equally remarkable are the results from the Keck and Gemini telescopes, imaging for the first time 3 planets around the star HD 8799. These are all gas giants, not Earths, but it's still wonderful to see other solar systems for the first time. It can't be long now before we find a planet like our own.
Well, that's about searching for planets, but what about life, particularly intelligent life? Well, over the years, the Sky Knights talked about this to some of the world's great astronomers.
But Dr. Shapley, there must be many worlds like the Earth in the universe. Surely some of them may be inhabited.
Well, by inhabited, I suppose you mean inhabited by living forms, things that we would call life. And the answer to that is, I think the probability is exceedingly high that there's abundant life scattered throughout the universe.
The presence of even a very low form of life suggests very strongly that in time an intelligent species will arise. Now this is simply because evolution in its course tries every possible niche, every possible trick which will enhance the survivability of a species.
The first essential is to establish that life out there really does exist, and at the moment we've no cast iron proof at all. So how can we set about searching? I asked Carl what sort of contact he had in mind.
Well, the kind of contact that I've been imagining is one by radio. A radio telescope at a remote site is running through a large list of stars, and one day star number 131,206 is looked at, and there is some clear signal, let's say the first 30 prime numbers, something like that. So there's no question that that is an artificial signal. And then interspersed with that announcement or beacon signal, there is at a very high bit rate, very high information flow, obvious content. And it will take us quite a while to decipher that content, and perhaps it contains the equivalent of the Encyclopedia Galactica, let's say.
The main organization looking for life elsewhere is SETI, the Search for Extraterrestrial Intelligence. Earlier this year, Chris went to California to see their new telescope array.
Hat Creek in northern California is home to the Allen Telescope Array, a very unusual telescope. It's listening for radio signals which come not from astronomical objects, but from alien civilizations. The receivers on each of these telescopes are so sensitive that the signal from a single mobile phone would overwhelm their delicate electronics. That's why they're here. The ring of mountains around me helps protect them from the hubbub of everyday life, mobile phones, microwaves and all. The telescope array is owned and run by the SETI Institute, a private organisation dedicated to the search for extraterrestrial intelligence. It's been a hard struggle, not least because governments are reluctant to finance a search for little green men. One of the central figures in that struggle is Dr. Jill Tarter.
As you can see, we've got 42 antennas and on our way to 350. And the idea is to build an array of a large number of small dishes because it allows us to look at a very large area of the sky all at once with very good spatial resolution. And we've built a telescope that can do SETI and radio astronomy at the very same time.
Because you can just piggyback on whatever the radio astronomers
We just share this big piece of the sky. And the radio astronomers are making images of galaxies or the hydrogen distribution out to 1 billion light years. And I'm in that same patch of sky finding stars to point the telescope to. We use different back ends, so it's all about silicon. It's all about digital signal processing.
And computing power.
We couldn't do this a decade ago, but now we can. Come on, we've got some Bombay doors here, and I'll open them up and show you. Right. Grab this.
Okay.
Ready?
Yep. Got it.
Now pull. And here we go.
Okay.
So now, if you look inside here, what you're looking at is the secondary reflector. So radio waves have bounced off the big dish up there onto the secondary reflector, and then they're focused back here.
Wow, look at that.
Isn't that amazing? I always think about Saturday morning television I used to watch. The Flash Gordon death rays. That's what that reminds me of.
So what is it? Why is it that shape?
That shape allows it to do two things. One, to capture very long wavelengths down here.
Okay.
So that's where the 0.5 gigahertz is picked up. It's like a car aerial that works at 0.5 gigahertz. Mm-hmm. And up at this end, the short wavelengths, the high frequencies, the 11 gigahertz, are captured by that part of the aerial. So now what we've done, we just put a little circuit board at the end of there, and we use electric traces, copper traces, to turn the signal around.
And then that's ready to head off into your base station.
We take the signal out here. There's another amplifier there. It goes as an analog signal onto fiber optics, which run down the pedestal and underground to the processing system. So that's our entire receiver cabin right here up front in the feed.
And easy to get to if anything needs fiddling with.
That's right, and very simple compared to a standard radio telescope. So keeping it simple was important if you want to keep 350 of these running.
And they look good too.
They look pretty out of this world, I think. I think it's quite appropriate for looking for alien signals.
And we want to do increments.
The array is used not only by professional astronomers, but by students, learning to analyse the faint radio signals it receives from the universe. It's not just celestial interference the team have to contend with. If a signal from another planet is picked up, they would have to be absolutely sure it's from another civilization, and not from something more at home on Earth.
The real challenge is not to find a signal, but to discriminate against what are our technology, signals from our own technology, and something that might be from somebody else's technology.
By our technology, you mean mobile phones, satellites, aeroplanes?
Microwave ovens, yes, exactly.
We've talked about these as if it's a deliberate signal you're looking for. Are we looking for aliens waving hello, or just side effects, just their leaking signals?
Well, it would be easiest for us to detect a signal that was being deliberately transmitted to get our attention. If you're talking about leakage radiation, if you're talking about a signal that's broadcast for some purpose that another technology has, it probably doesn't have a lot of power in it because it's meant for local consumption. So when we broadcast television or radio signals, we only put enough power in them to reach the next county. We don't put enough power in to reach the next star, right? Because we don't have an audience out there.
So bearing that in mind, where do you look? Which stars are you going to target?
Well, the way we do radio SETI has two different approaches. One is to say that we pick out stars like the Sun, where we know there's a habitable planet, and we start with the closest ones to the Earth, because we could hear the faintest signals, and then we work our way out. So that's one way. That's a targeted search. There's another approach, which is instead do a search of stars, because we think that planets are necessary, and planets are orbit around stars. So let's look where there are the greatest number of stars. And we're planning a search along the plane of the galaxy towards the center of the galaxy, so 20 square degrees of the sky will be surveyed. And in those lines of sight, along the distance to the galaxy, there's somewhere between 4 and 10 billion stars. Now, most of them are very, very far away, which means that if there's a transmitter there, it's going to have to be really knock your socks off strong for us to detect it. But that's an experiment we haven't done. And so if the planet with the transmitter is sitting at the distance of the center of the galaxy, that transmitter would have to be 20,000 times as strong as the Arecibo radar, our strongest signal. But that's not outrageous, perhaps, for an advanced technology intending to try and attract our attention.
What about your gut feeling? Have you got any feeling for whether we're alone in the galaxy or not?
I actually don't have any answer to whether we're alone or not. As a scientist, it wouldn't matter what my gut said or what my belief said. Belief is a verb that belongs with religion. We're talking about evidence and data and scientific exploration. The only thing that you can say about that is something very wise that Philip Morrison and Giuseppe Cacconi said as the last sentence of the 1959 paper in Nature, first paper ever published on SETI. What they said was, the probability of success is difficult to estimate. But if we never search, the chance of success is zero. So around here, we're going to keep on searching any way we can with whatever technology comes along.
The completion of the remaining telescopes depends on obtaining further funding. SETI's always been an audacious long shot, but it's hard to think of a grander stage for human ambition than trying to say hello to our neighbours, assuming they're out there.
We've been talking about planets of other stars, but what about planets in our own solar system? Pete Lawrence is outside in my beloved dome to tell us what's on view this month.
There are a number of bright planets on view throughout December, but to see them, you're going to have to go to either end of the night. Just after sunset, if you look towards the southwest, there is a very brilliant planet on view, and that's the planet Venus. It is intensely bright and very difficult to miss. If you watch it for a while, you'll see that there is another bright dot immediately next to it, and that's the planet Jupiter. They're very close together at the start of the month, but then they gradually move apart, and you'll see Venus get higher in the southwest after sunset, while Jupiter moves down into the evening twilight. If you can catch them by the end of the month, around about the 29th, Mercury comes up to join Jupiter. In fact, on the 29th itself, there is a very thin crescent moon there as well. So if you've never seen Mercury, this is a good time to try and spot it. The other planet, which is on view throughout the month, is Saturn. And to see Saturn, you're going to have to go to the early morning sky. It rises at about midnight at the beginning of the month, but you need to give it time to get a reasonable altitude in the sky. So observe it, say, 2 o'clock, 3 o'clock in the morning. It's quite easy to find, and to do so, we need to use one of our old friends known as the plough, or as I like to refer to it, as the saucepan. If you can locate the stars that make up the saucepan, locate the two which are at the left-hand edge of the pan, those are the two closest to the handle, and extend the line they make down towards the horizon. Eventually, you'll come to a fairly bright star, and that star is called Regulus. It's the brightest star in the constellation of Leo the Lion. You can confirm you've got the right star because immediately above it there is a backward question mark pattern of stars, which is known as the sickle. And this is supposed to represent the head of the lion. Now, the body is marked by a rectangle heading off to the left of the sickle. If you can find the two stars at the back end of this rectangle, the left-hand side of this rectangle, below them lie the lion's legs. The star which marks the rear paw is known as Sigma Leonis, and right next to it there is a yellowish, quite bright star. And this isn't a star at all, it's the planet Saturn. Now, if you look at Saturn through a small telescope, you normally see the magnificent ring system. That's one of the main features of the planet. But at the moment, you're not going to see the ring system. And there's a very good reason for this, because the planet is tilted almost edge on to us. If I can explain with this little model here, normally we recognise Saturn as looking something like this. And about 15 years ago, the planet and its rings were fully open to us. But as it goes around its orbit around the Sun, as we see it, the planet gradually changes its inclination. And the tilt at the moment is virtually edge on. So if you look at the planet through a small telescope, the rings are extremely difficult to see. It doesn't mean that there's nothing to see around Saturn. In fact, there's plenty to see. If you look at the globe, you can sometimes see white spots, and these are storms in the atmosphere of the planet. And they move around the planet quite rapidly in a time period, say, of several hours. The moons of Saturn are also well on view at the moment, again because the rings are out of the way. And the brightest moon, Titan, is actually bright enough and moves far enough away from the planet that it can be seen with just a pair of binoculars. So even if you have binoculars, a small telescope or a large telescope, get yourself outside throughout the month of December and have a look at these wonderful planets.
Pete, thank you very much. Now back to our news notes. Chris Beck, of course. Now there's exciting news from the planet Mercury. A messenger is going around and has made a second flyby. And welcome now to Dr. Dave Rothery from the Open University. Well, Messenger is doing very well.
Yes, Messenger flew past Mercury for its second time in October and saw most of the globe which had hitherto not been seen before. So we now know the general geography of Mercury, and we know about the extent of the lava plains on Mercury. Now, Messenger, in its flyby earlier in the year, revealed that areas which are quite smooth are definitely covered by lava. There was some doubt as to what it was, but volcanic vents have now been seen on Mercury. So these smooth plains, so-called, on Mercury, with wrinkle ridges over them, are lava. A very long time ago, there were no erupting volcanoes, but it's very largely sculpted by volcanic forces.
In some ways very like the Moon, in other ways very unlike.
Well, yes, the volcanic plains are similar, except they don't stand out and hit you in the eye. If you look at the Moon, you've got the dark patches, Vimario, where there's such a strong albedo contrast. That doesn't happen on Mercury. For some reason, the lavas are poor in iron, and that makes the colour much less dark than it would otherwise be. So you have to work hard to work out where the lava is and where the lava isn't. And it turns out that the lava is almost everywhere on Mercury.
Now, Messenger's have been round twice, sending out new data each time. There's a third pass next year, and then, of course, it goes into orbit.
Yes, going into orbit is the really exciting part of the mission from now on. Once in orbit, we can re-image areas of the surface under different lighting conditions, see it in stereo, begin to deploy things like the X-ray spectrometer, which will map the distribution of elements on the surface of Mercury, map the topography. You know, orbital missions are much better than flybys. Not so dramatic, but in the end you learn so much more.
So we are, at last, solving some of Mercury's secrets.
I hope so.
Well, Messenger is doing very well, but one rather sad piece of news on Mars. Phoenix, I fear, has come to the end of its career.
Yes, and we always knew this would happen round about now. It's a little earlier than we'd hoped. Phoenix, remember, is the lander that touched down in the Martian Arctic, a very hostile, cold environment, and has been exploring the soil and the water ice that they found underneath that soil.
With great success.
Yes, absolutely. All sorts of things we've learned about this environment. We knew there was ice there from orbit, but Phoenix has been able to dig down, touch it, scratch it, sniff it, put it into little chemical laboratories on board. We've discovered all sorts of things. They found some strange salts, some possible clay-like material. They've discovered the soil is alkaline. They'd been expecting an acid soil, but it's not that at all. It's alkaline, and there are many mysteries. The real work of analysing the data is underway, but the winter's drawing in, and sadly, just at the start of November, we received our last transmission from Phoenix.
I wonder,
the spacecraft is dead.
Is there any hope of reviving it, do you think? I would say not, but...
Well, there's always some hope, and they will be listening for at least the next month, and then at kind of towards September 2009, once this area starts to reach spring again. But I'd say there's almost no hope. What's happening is the days are getting shorter and shorter. At some point, there'll be a long period with no sunrise at all, just like you get at the North or South Pole on Earth. In fact, where Phoenix is sitting will probably end up under the polar cap.
I'm afraid it will.
But we can monitor this from orbit. So we've got the observations from Phoenix over the last few months on the ground, but the Mars Reconnaissance Orbiter will be keeping a close eye on changes from orbit. So we will see the frost appear and we will see the ice cap grow, and that will tell us a lot.
Eventually, I'm quite certain they'll go and dig Phoenix up.
Yes, well, let's hope so.
Dave, Chris, thank you very much. Now, next year is the 400th anniversary of the telescope. And next month we're doing a special programme about it. So until then, good night.